After all the other videos on this topic, I thought maybe it'd be nice to look at some of the actual writings on this MRSGS topic. So this is how it started, was with a letter that I intended to send to a few mathematicians who might find it interesting, see what would come of that. I certainly find it very interesting. However, the letter slowly but surely grew longer and longer and longer to the point where it's quite considerably too long for any decently lengthed letter. So it ended up becoming more of a monograph. In this first rendition of the now is monograph, yeah, I had a little less formal approach because, again, it was intended to be more of a letter. Not entirely informal, after all. It is about mathematics, and it was meant to be somewhat technical. But yeah, and of course, in the monograph itself, it's going to be much more so technical, and conform to some of the various traditions in the mathematics monograph world. Right. So, for example, this is now written in LaTeX, whereas previously this was written in a word processor. And so you can see it looks quite a bit nicer already. And yeah, very excited about its new and wonderful presentation quality here. And it will look more along the lines of this, the sort of thing you would see if you were to read an article or a book in mathematics, often certainly a monograph within the fields of mathematics. So yeah, I'm very happy to see it coming along, looking very nice in the LaTeX format. Which, by the way, in case you're not curious, in case you're not familiar with LaTeX, that's just essentially it's just a software used to essentially code a more technical writing. So yeah, it has many benefits, such as being able to present formulae and theorems and such things, and proofs, mathematics notation, in a much nicer sort of looking format. And yeah, so it's really neat, and I'm quite excited about it. So yeah, that said, it's not quite at the point as far as length goes just yet, as the less formal letter is. Not even this printout. So let's go ahead and look at the letter just to kind of speak through some of these topics instead. So yeah, here we go. Now you'll notice, as this is less formal, and it's not even a final draft, it's more of an nth draft as n approached infinity. Still is. But yeah, so this is some notes here. There will be notes. There are some notes in here. It was intended to be a final draft eventually, so you will see some footnotes and such. At any rate, yeah, so it's not untechnical, that is to be sure, it is not. But, it is less formal than the monograph will eventually be. At any rate, let's just kind of look through it, because we're not going to even get this technical. So it's just a video kind of walking you through some of these ideas, and not meant to really bog you down with any mathematics with which you are not familiar or prepared to discuss. So for example, here, the very zeroth section, I preferred zero indexing for various reasons. At any rate, one-to-one correspondence between, for example, the residue sequences and the MRSGS, the graphing systems themselves. So that is established here in both directions, and then thus their one-to-one correspondence. And also the reason is spoken of here, less formally, as far as using the concept of localized vectors, which I did mention a little bit before, and won't go on too much here either, but they simply stated here, vectors, as many of you might very well know already, vectors generally aren't considered to have the property of location, and yet much less frequently. You can find some previous work where localized vectors are used, and that is to say vectors with the added property of location. That is what is meant by the word vector from here forward in this video, in this paper, and then so on. One might have also used a term like directed segments or disegments for short, but yeah, we'll just go with the term vector in the sense of localized vector. Okay, and then location within higher orders of lattice graphs of MRSGSs. We don't need to get into the technicalities here, but that's what this is about. Speaking of location and making that more formal. Some examples, which you might recognize a bit or seem familiar, yeah. Even the concept of an origin in MRSGSs is addressed a little bit more technically here, even though it's really just the center of an MRSGS graphing system. First order lattice graphs, which we did see a bit of, and the ideas of absolute and relative, we spoke of in a previous video. And second order lattice graphs and vector equivalency classes we did not speak of, and we will not speak much of. Well, we kind of mentioned them in passing, where you might end up at the same place if you just rearrange some of the terms in a given sequence. We're not going to speak much at all about lexicographical ordering of n-tuples. This is just to establish a way to refer to those equivalency classes. Anyways, so, and then vertices within the lattice, we did speak a little bit about points, I called them, much less formally in a previous video, existing in a sense within these MRSGS lattices. This makes that more formal, using the term vertice instead of points. And it can be used and is a very useful concept, and this is making that more official. Right, and then, so there's these sort of self-covering lattice graphs, where you'll notice, like in the mod 4, we get less of this really complicated stuff happening, basically, because it's the lattice itself is actually going over various places it's already been, whereas this doesn't do quite nearly as much of that. So every time you increase the level or the order of the lattice, of a given MRSGS, you end up with much more complicated, quote, graph paper, end quote, whereas in these cases you do not. Well, not visibly. So, and more notes. So, exponential growth, we kind of, basically implied here. Even this is included just to show how ridiculously complicated the quote graph paper end quote of mod 7 MRSGS is, even up to 7 levels. It's just completely filled in. It's not at all helpful to look at a lattice with this much complexity as graphed, that way. So and this is not too complicated, just an explanation of that exponential growth of these lattices, and then the sort of rationale justification for using radial rays, which we did speak of in a previous video, instead of actually showing the entire lattices, which are almost ridiculously complicated in many cases, rather soon. Okay, so and then this goes into the concept of radial rays, and here are some of those just shown by themselves. It's just much easier to look at this than it is to look at that. And yet we're describing the same idea here. This is still mod 7 mod 7 RSGS, but we're displaying just the radial rays, wherein we can go ahead and also display a graph. Here, this is showing the entire lattice graph up to the same level, but instead using the entire lattice, which, again, is somewhat absurd. So just a little rationale for using the radial rays notion, even in something less ridiculous looking than this one. Still, nonetheless, I think less cluttered. And levels and residue stars we spoke of. You might even recognize these if you saw those videos, or that video. And there we go. And we even spoke of the idea of the levels being related to the minimum number of vectors required to get to a given level. That's actually what this is about. We don't need to worry about the exact notations or anything here, but just, the level related to the minimum of the, anyways. There you go. You might recognize that topic. And here we have some residue stars, which we did look at a bit. And some residue stars up to a higher level within some MRSGSs. And many pardons for the descriptions of these images not quite lining up there on the page there. Not sure where or when that happened, but I'm just kind of rolling with it. I hope you don't mind too much. This is not the final draft after all. At any rate, residue star enumeration, equivalent residue stars and n-gonal loops is this next section here, starting with residue star enumeration from the n-tuples. N-tuples, by the way, is somewhat fancy talk, you might say, for how many terms there are in a given sequence, essentially. So if there are n terms, then it's an n-tuple, right? So we have 3-tuple if there's 3 terms, and so on. At any rate, there are multiple interesting things about n-tuples. Anyways, we'll move on. This is a formula to derive something related to that topic. And moving along. So many interesting images are included here. And definitely check out the link in the description if you're interested in looking through this less formal letter rough draft more thoroughly in your own time, provided in the description of this video. And residue star equivalence via permutations. This is a more formal writing on that. Not quite as formal as the version coming from LaTeX soon. And 2-gonal loops. Turns out we have this idea of loops, which we kind of looked at without mentioning it in a previous video. But what is that about? Well, you can have a sequence that let's see, I'll get a less trivial example. The trivial examples can be a little confusing. Okay. These are the trivial examples. So I'm getting no non-trivial examples here. Here we go. So this is an odd n-gonal loop where we have, it's a loop. It goes around and around and around. Right? Or at least it closes back in on itself. Creates a loop. So it's really quite a basic concept, essential idea as it goes. The loops themselves can become much more complex as you go on. And so there's some more on that than just that they come back in on themselves. It's really nice looking loops in there. Yeah. And moving along, this is more technical stuff you don't need to worry about in this video. And so just moving straight through that. Those mathematically more inclined, feel free, again, to check this out in your own time. But so equivalence of residue stars with multiple n-gonal loops, just forming an equivalency between other objects in these lattices. Residue stars, and okay, so we kind of looked at these, yeah, and we saw some of these examples in a previous video. Yeah, and just quick, I guess, for what it's worth, without getting technical here anyway, is the equivalency. You might have this residue star be labeled S1, but in another perspective, it could also be seen as an S3. So, anyways, don't worry about it. Yeah, so yeah, but we do need to deal with these topics as we go through this in a more technical manner, because they just naturally arise as we, look more closely at these MRSGSs. So yeah, these equivalency classes must be considered. More notes. Okay. And yeah. So moving along, okay, yeah, this is a perfect example of something that won't be included in the final draft. It's an incidence matrix, but it doesn't look too great. It didn't quite come out the way I hoped. I'm leaving it here in the rough draft just because it's, important to the topic, but in the final draft, which will look much nicer, it'll look much nicer if or when it is included. Yeah. So, isolated vectors, segments, and vertices within MRSGSs, I mean, without getting technical here, it's really kind of pretty basic idea. We can talk about a particular vector or point, what have you, vertex, within a given MRSGS by specifying a level, a residue star within that level, and a residue within that residue star within that level. So with just those three numbers, these are variables to represent those values, right? You can identify a given vector, segment, or vertex within a given MRSGS. So it's essentially a coordinate system, to be able to speak of various vectors. That's fun. Various vectors. Anyways, so to be able to speak of various vectors within MRSGSs without having to specify the entire previous, sequence or terms of the sequence to get to where you are. So, anyways, you can speak of just specific locations within a given MRSGS using these values. And it goes into more depth with that. And again, some notes there. Yeah, and there you go, and a little bit about modular lattices, which is a topic you don't need to worry about at all. Yeah, so. Okay, so graphs of sequences in MRSGSs. This is now going into a sort of second section of the whole thing, where I'm actually showing some of the graphs within the graphene systems. So yeah, so there we go. And these are just some constant sequence graphs. So like a sequence 2, 2, 2, 2, 2 forever, might look like that in an absolute system. Well, this is for mod 5 RSGS, right? Just kind of goes that way forever. And, sequence 4, 4, 4, 4, 4, 4 forever, does that rather expectedly. And so, yeah, just a constant sequence. But now in a relative mod 5 RSGS, we'll do something somewhat different. Where if we have the sequence 1, 1, 1, 1 forever, right, then we end up with this nice pentagon. And then over here, we end up with this pentagram with the sequence 2, 2, 2, 2, 2 in the relative system, which remember means your zero direction, if you will, is determined by the direction you're facing at any given time. So here we have 0, 1, 2, but now if we went this way, which we did, now 0 is this way, and so 0, 1, 2 will end us over here, and so on, and we end up with this lovely pentagram. And with 3, we end up with a pentagram again, but over here. Upright instead of downright. Upside down. Anyways. And then we have this pentagon, but we'll get into details of that. So, yeah. Constant sequence graphs in an absolute mod 7, so just increasing the modulus value to see what happens. That's one of the fun things about these MRSGSs, is that you can change various things that you're looking at not only can you change the sequences, you can maintain the same sequence, whatever it is, Fibonacci sequence, whatever, and then change the modulus, for example. Stay in absolute MRSGSs and just change the modulus and see what it does in various moduli. You can change from absolute to relative, and see what happens. And so there's more than one way to see the same sequence, even within MRSGSs, right? So that's kind of nice, I think. Huh? And so that's what is just going on a higher level of moduli. I shouldn't say level because that's the term we're using for other things. But so there we go. Anyways, and so instead of a 5-pointed star, you end up with this cool 7-pointed star shape, or this 7-pointed star shape with a 3, 3, 3, 3, 3 forever in mod 7 RSGS. Notice we're using the entire lattice here as opposed to radial rays to show them. I think it's nice to see in this context because you can see of all the things it could have done, it did that. So here we have just observations made on some of the previous topics included in this paper up to this point. Generally speaking, these observations are, in case you do look at this paper more closely, are directly related to the exactly previous topic. And so in this case, we're talking about closed and bounded graphs and polyskeletons and relative MRSGSs. Don't worry about any of that much, except notice that the closed idea, the bounded idea, those two are relatively familiar terms if you've taken some calculus. At any rate, polyskeletons probably not so much, but if you pick up the book Turtle Geometry, you will find the term polyskeleton used, which is rather convenient because it turns out to be important for these MRSGS graphs. So I was quite happy to take that already coined term. It's quite a fancier term than I would dare use here, coming from left field as I am here with this whole thing. Well, from the perception of some. Yes, and understandably so. But anyways, moving on. Yeah, so that's what this is about. It's a rather interesting topic. And then, integral linear sequence graphs. So, we're just sort of increasing from not merely constant, but, linear sort of sequences where we might have it increasing. Just linear, gosh, I can't say linearly. Okay. Yes, okay. But, a sequence which is, 0, 1, 2, 3, so on, And this is the absolute mod 5. Now we do have this sort of closed, graph occurring. And we're not going to talk about the negative indices much here, It's the same. It's just, okay, might as well real quick, We can have a sequence that comes up from negative infinity and then goes off toward positive infinity, or it could start somewhere. Anyway, that's the idea. So, and here in red we see the negative indices, terms of the negative indices, and then the terms of the positive or non-negative indices there in green. It's rather neat to see how they spin around when you just shift that sequence, if you will. Start at 0, start at 1, start at 2. Anyways, neat. And congruence of graphs irrespective of location. That's just fancy talk for saying, for example, this graph and this graph are rather similar. In fact, they're the same. They're just in a different place. So, or, this whole thing taken as a graph and this whole thing taken as a graph are rather similar, except different orientation. Right? So that's the idea. Just your usual idea of congruence from your geometry class, And here we have integral linear sequences in relative mod 5 RSGS. And so again, we're just looking at sequences that aren't constant. It's like, 0, 1, 2, 3, 4. Like this one is repeating over and over again, just that. In mod 5, because that's what, anyway, I'll leave out the details. That's what would happen if you just had like a y equals x type function over mod 5. And if you do that in an absolute, make sure that's what we're doing here, relative, pardon, mod 5 RSGS, you would look at a graph that appears in this way. And yeah, so anyways, shifting things over again, where you get, the same y equals x plus 1 would give you this sort of a looking thing. And notice some similarities, just a different starting point type looking thing. But then plus 2, we end up with this, still pretty similar. But then plus 3, now it's looking pretty different. So some interesting behavior, even with just some slight changes. Okay, so yeah, and even in a simple sequence of that sort. At any rate, integral linear sequence is an absolute mod 7 RSGS. And so we're looking at the same idea here, but now it's in mod 7. And there you go. And then again here, but now we'll be looking at that in, it looks like the relative modular, oops, that's not doing that what I wanted, but okay, well, relative modular residue sequence graphing system. Yep. And there we are. Some interesting graphs that come of that. And again, we're looking at things like y equals x plus 6 here over mod 7 as portrayed in a relative, mod 7 RSGS. And so we come to this idea of parent graphs to kind of speed through some of these more polynomial type functions and their respective sequences as portrayed in the MRSGSs. Parent graphs is, if you've taken Algebra 2 here in the US, sometimes it's referred to as advanced algebra, but not the college variation, high school variation, you'll have studied parent graphs, hopefully. And you will know there are certain functions that have their simplest version or variation, right? So like, for example, y equals x squared is the simplest of the quadratics. It could have been y equals x squared plus 2x minus 1, but no, it's just y equals x squared. Done. It's the simplest variation of what it has to be considered quadratic at all, right? So that's a parent function. Well, likewise, we have this sort of corresponding concept in MRSGS's parent graphs. And so, looking through this, we're looking at some linear varieties. And moving on to show some of the higher degree. Well, I do recommend taking a look at some of these graphs. They're very nice. Yeah, and then integral polynomial sequence graphs. So, never minding much else about that, except that notice here we have n squared, which would have been a parabola, right? And this is how it looks in a absolute mod 5 RSGS, which kind of looks neat, I think. Cubic function, which has that sort of cubic shape. Yeah. Well, in this mod 5 context, in the absolute variety of the RSGSs, we have this happening with the negative indexed values here and the non-negative indexed values here, repeating this shape over and over again. Pretty neat. And here we have quartic, which notice doesn't give us that convenience of a closed graph looping around over and over again. Here we have n squared again, but this is an absolute mod 7, and it does this thing, trailing off the screen or graph paper, or however you want to conceive of that, toward our quote infinity end quote. And n cubed. Again, just taking integer values for n, cubing them, and then taking over modulus 7, graphing it in our absolute mod 7 RSGS. We end up with this for the non-negative values, or indexed values, and this is what the negatively indexed values do before that happens, if you take them in least to greatest order. So yeah, just some fun stuff to look at here. And here's a nice one, what I think quintic parent function, n to the 5th power mod 7, and it does that. Pretty neat. And this is the 6th power, right, parent function, right, n to the 6th mod 7. And yeah, so, just looking at various properties that come out of that, we without too much effort, see something that might be referred to as non-polyskeletal closed but symmetric graphs. Not worrying about what that even means, but I think to just notice here that it actually relates to something called Fermat's little theorem, which is neat, and just a nice little bonus there. And if you don't know what that is, you can look it up if you would like. It's rather well known in a number of theories, so if you know that, you might know that. Anyways, integral polynomial sequences in the relative mod 5 RSGS. Just some more examples of some graphs of this, parent graph variety. Moving along. Here we have relative mod 7. And this is just what would have been a parabola, right, in an XY Cartesian coordinate system, n squared. But this is over mod 7, relative RSGS, and it looks like this instead. So I think that's nice. Yeah, and here's I want to say it right, quartic, yes. I don't want to say it as often as the other ones, right? Fourth degree polynomial, the parent function thereof, y equals x to the fourth power, right? Type thing, and it does this in mod 7. In red again, these are the negatively indexed values coming from negative infinity, and then non-negative values doing that in green, and then in blue. Green's the motif of the blue. Yeah, so it repeats that over and over again. Cool. And so yeah, this is 5th power, 6th power. Really interesting things happening there. Now, as much as I was reluctant to, or practiced the reluctance to, coin new terms, if whenever possible, always seeking previously used or currently used, any other, instance of a related term, so that I could use it in the same way. As much as I practiced the reluctance to coin new terms, I nonetheless kind of felt like I needed to on occasion. And so this is one of those cases where I, like, for example, motifs. Actually right here, I even mentioned it. Let's look at this one though, for example. This in green is what you would call the motif of this graph. Because why? Because, well, it does this over and over again, and as it goes off towards infinity. So that's the motif. Right. What happens as it does that is another question. Is it closed? Does it loop back in on itself? Does it go off to infinity? There's different possible things that can happen with a given motif as it repeats, but nonetheless, the term motif is useful. So I went ahead and coined that one for this purpose. Always trying to be careful not to step on anyone's toes as far as other uses of the term, for example, of motif. But, if for when that ever did occur, I try to make sure that they're not directly related fields of mathematics, at least. So, otherwise the confusion would be not excusable. And I just find a different term. At any rate, so here's some more technical stuff we don't need to worry about. And, periodic continued fractions and their graphs. If you're not familiar with periodic continued fractions, rather, don't worry about it. It's a cool concept. Basically, if you love fractions, you'll love continued fractions because they go on forever. Anyways, these ones are periodic as they do so. And so one of the neat things, just quickly, is that you can represent these quadratic irrationals, they're called, just square roots, of numbers that turn out to be irrational, with these periodic sequences, that repeat over and over again. And you can actually compute those values of these irrational numbers using this periodic representation, which is really neat. At any rate, so I thought that would be cool to look at in terms of the MRSGSs, and turns out they were. And so, just looking at some of the graphs, okay, maybe some of these graphs are cool to some and not to others, but I think so. At any rate, and then some other things that happen, that are worth looking into. As you, for example, increase the modulus value of the same, using the same sequence, right? In the same otherwise relative or absolute, sticking with one or the other. You sometimes see these sequences sort of approaching what look like a radial ray, or bounded around what could be conceived of as something similar to a radial ray. I'm not going to get technical. It's hard sometimes to speak without getting technical at all, so I'll just leave it there. Never mind. They basically start turning into something that looks like a straight line sometimes, or a radial, or a ray, rather. Yeah. Wow, that's hard sometimes. Okay, so moving on. Here's some more fun graphs of the periodic continued fraction graphs. This is square root of 14, by the way, which is irrational. But we have this neat little periodic continued fraction where you start with a 3, and then you just repeat 1, 2, 1, 6 in this PCF, periodic continued fraction, context. And, well, anyways, graph those terms as a sequence, and there you go. This is in mod 3, if you do that. This is in mod 2, which just kind of does that over and over again. This is in mod 4, which makes that. It's neat. This is the motif in green, and then it does that, and then it keeps doing that. And this is in mod 5, where this is the motif, and then it repeats that over and over again. This is mod 6, where that same sequence now looks like this, and looks like this in the mod 6 RSGS. Kind of nice. And this is in mod 7. Notice the green again, motif, repeating that shape over and over again, gives you this closed graph, in this case, as well as this one here, with, in this case, this motif. Right, so yeah, so some very interesting topics that we can speak of, building off of the idea of polyskeletons, are addressed as well, such as polyskeletal boundary graphs, or polyskeletal classes, and then something called jumps, which we don't have to worry about here. Yeah, so it's not exactly a informal as far as depth is concerned letter, so just keep that in mind if you do decide to look through it. But you know, yeah, I'm certainly not going to tell you not to look at it. It's very interesting, certainly, if you ask me. So clearly, yeah, some other interesting stuff. You know, these closed graphs, some of them start looking more like circles, to put it simply, as you increase the moduli toward infinity. So that's more technically putting that one there. Periodic continued fractions for a different value, such as the square root of 1001. And starting with absolute MRSGS's, we get this repeating periodic, right, sequence, and then we take that over various moduli, and we graph them, and we get these rather very interesting graphs. Yeah. And we're not going to talk about superimposed MRSGS's of motif resultant graphs. Well, maybe just quickly. Okay, well, shall I try? Okay, motif resultant graphs. You know, this... Yeah, no, it's not. Okay. Okay. I tried to try. Let's leave it at that. Okay, and then so anyways, yeah, more on that. And if you happen to be one of those who might be watching this video, who are already more familiar with mathematics, do feel free to check on this bounded F5 symmetries, concept here. Yeah, so there's the idea, and it gets into more detail, more depth there as we go along. Just try to analyze these graphs in some kind of meaningful way. Try to develop some way to speak of them or think of them that relates back to the sequence, and hopefully, to some properties of the sequence that even more hopefully might not have been noticed before, right? So that's kind of the idea, right? Visual representations can often lead us to, at least if nothing else, refined intuition on some of the objects of mathematics that might otherwise be more abstract. Right. So yeah, so this is the idea here, and it gets technical here. Okay, so and yeah, we're not going to do that either. And so yeah, we just kind of left it here for now. But yeah, so that's a bit of a glance through this letter version of the MRSGS monograph, as it will become soon. Hopefully sooner than later. Yeah, and when it does, it will look more like this. Thanks be to LaTeX and its wonderful ability to present things in a much nicer sort of format. So yeah, so that's the idea here. And MRSGS is very exciting. I never thought that I'd be spending so much time on this topic. I didn't even know it existed until I tried to put, together or to reassemble that program that my brother made for me in high school. And, again, in the process of doing so, I ended up, saying, what's with this turtle geometry thing? What's the simplest thing we might do in this environment? And, well, there you went. Yeah, MRSGSs.